Modern programmable ASIC switches operate at the terabit scale, moving billions of packets per second through a single piece of silicon. Their primary function is rapid, stateless forwarding, pushing data packets from point A to point B as fast as physically possible, without analyzing the broader context of the connection. Modern networks operate on more complex requirements. They rely on load balancers, rate limiters, and sophisticated packet schedulers, network functions that require stateful operations to understand the ongoing history of a connection. To execute these stateful operations, the hardware must track active flows over time. Tracking these flows requires physical memory space on the chip. On a standard ASIC chip, real estate is strictly limited. The high-speed on-chip memory, known as SRAM, typically caps out between 10 and 100 megabytes due to die space constraints. This diagram compares available memory to actual operational requirements. A modern 25.6 terabit-per-second switch has to handle around 120,000 active flows for every gigabit of traffic. To maintain state for a standard load balancer at that volume, the hardware needs roughly 52 gigabytes of memory. The problem extends to processing power. The control planes on these high-speed ASICs have a hardware ceiling. They peak at about 100,000 table updates per second. Terabit traffic demands millions of updates every second. That 52 gigabyte memory requirement is hundreds of times larger than the physical SRAM limits built into the silicon. The constraints of physical die space and processing capacity make it impossible to house complete dynamic flow states directly on the chip. The standard engineering workaround is to route the complex network functions away from the switch and onto dedicated external CPU or FPGA servers. In a typical setup, the switch takes the entire data packet, often up to 1.5 kilobytes in size, and routes it across a physical link to the external server. To make a routing decision, a stateful load balancer usually only needs to read the packet's 5 tuple, a tiny header roughly 13 bytes long. The remaining 1.4 kilobytes of payload data are functionally irrelevant to the logic. To select a destination server, the processor only needs the identifiers found in the tiny 13-byte header. Dragging that weight creates an immediate traffic jam. The external server's network interface card and its internal PCIe lanes become saturated with irrelevant data. To compensate for these choked lanes, network operators are forced to assign massive numbers of expensive switch ports solely to maintain connections with additional external compute nodes. Adding more processing servers fails to solve the root problem. Routing massive payloads physically chokes the external links long before the CPUs hit their processing limits. A system called ribosome bypasses this hardware ceiling by physically decoupling the packet's routing logic from its storage weight at the switch level. The operating philosophy relies on strict data hygiene. Transmit and process only the specific bits required for the logical operation. Upon receiving a data packet, the programmable switch acts as a physical separator. It inspects the incoming data and severs the packet precisely at the 72-byte mark. The switch immediately generates and attaches a unique matching ID tag to both the newly separated 72-byte header and the remaining payload chunk. The switch logs the original header into a specific slot, or index, within a circular SRAM array. This array is highly compact, requiring less than 60 kilobytes of memory. The switch routes only that tiny 72-byte header across the port to the dedicated external server for processing. By stripping away the heavy payload, ribosome eliminates the PCIe bottleneck entirely. The external CPU receives exactly the data it needs, preventing memory cache pollution and maximizing throughput. While the header is processed externally, the massive payload chunk remains at the switch. These payloads require no active CPU computation. They are pure bulk data that require temporary storage until the routing logic is determined. Instead of consuming dedicated hardware, ribosome routes these payloads to shared general-purpose servers within the data center, machines already running other customer applications. It executes this transfer using a protocol called RDMA, or Remote Direct Memory Access, over ROX v2. The core advantage of RDMA is that it allows the switch to write the payload directly into the shared server's memory bank, entirely bypassing the server's processor. The network utilizes spare NIC bandwidth and unused memory space, leaving the server's primary workloads completely undisturbed. To protect host applications, the system includes a control plane failsafe. If a shared server's link hits a defined bandwidth threshold, ribosome triggers an automatic cutoff, stopping payload transmissions to that specific machine. This architecture transforms the data center's idle memory into a massive programmable packet buffer at zero computational cost. Back on the dedicated server, the stateful processing on the 72-byte header finishes. The server transmits the modified header back to the programmable switch. The switch receives the packet and matches the returning header ID against its local SRAM array index. That match fires an immediate RDMA read request straight to the shared server seconds, which is significantly faster than the time it takes the switch to loop through its array of index slots at terabit speeds. The payload arrives at the switch, merges perfectly with its modified header, and the fully reassembled packet routes out to the network. By retrieving the payload in just 4 microseconds, the system ensures the stored header is used and cleared before the circular array loops back to that same index slot. This timing allows the switch to process terabit traffic without overwriting active data. The quantitative performance data shows the specific advantages of this architecture over legacy methods. This chart plots output throughput against input rate. Notice the traditional offloading systems routing full packets. They flatline hard at a 100 gigabit per second ceiling. The cap occurs because the external physical link bandwidth saturates. Additional processing power on the CPU cannot fix a saturated physical wire. The separated architecture scales linearly past that barrier, achieving 300 gigabits per second of stateful packet processing on a single server. This result requires a minimal dedicated footprint, just a single 100 gigabit interface on the processing server, supported by 4 shared RDMA servers holding the payloads. This bar chart extrapolates that port efficiency. To process 1.6 terabits per second, a legacy setup demands 16 dedicated switch ports. This architecture requires dedicating only 3 switch ports to logic. Physically separating the logic stream from the storage weight solves the hardware scaling bottleneck. There is one final engineering constraint: ensuring that splitting and reassembling packets doesn't scramble complex, order-dependent traffic. A strict test case is a packet scheduler known as reframer, which relies on intentionally buffering and reordering packets based on specific flow priorities. The risk is that the remote RDMA servers might answer read requests out of sequence, destroying the scheduler's logic upon reassembly. To prevent this, the processing server assigns strict queue-pair sequence markers to the headers. These markers map directly to specific queues on the RDMA servers, forcing the remote memory to output the payloads in the exact deliberate sequence dictated by the scheduler. When running the reframer scheduler, ribosome reaches 220 gigabits per second. This is a 2.2 times increase over the original implementation's 100 gigabit limit on the same server hardware. Reaching the terabit threshold for stateful networking requires physically separating the routing logic from the bulk data storage.